Okay, now. Only about half the people actually sketched a graph of the 2 to the x function, okay? So I prompted you and then got some pretty good sketch, okay? So your first impulse when you're talking about a vertical stretch of a basic function ought to be sketch that graph. It can't hurt you, and it shouldn't take you more than a minute. Time me. Okay. You should be able to construct these graphs of any basic function this quickly. It will be helpful when you get to an exam in the pre-calculus course, okay? And it's something that I've stressed from the very beginning. Now, in my course, it's more important than in some other courses, but every course starts off with your 2 field basic functions, okay? Parent functions, whatever they're called. So this is your y equals 2 to the x function. Now this function, let's just say that a is 3.5. I don't know if there's anybody who has 3.5 letters in one of their names. It'd be kind of hard to do, but let's just say that a happens to be 3.5. In your case, it'd be an integer. But if a is 3.5, then you got to go through 0, 3.5. So your exponential function is going to be more like this. So this is y equals what? It's a times 2 to the x. Why is it a times 2 to the x? Because it's a vertically stretched function. That's how we sketch y equals 2 to the x, our basic function. The vertical stretch of the basic 2 to the x function, so the equation y equals a times 2 to the x. Okay. Now from this picture, can you tell me what a has to be? Can I record any of that? Apparently not. I'm going to say it again. It's worth hearing again anyway. Well, apparently I didn't record all that, but let's just make sure we understand it. It'll go by quicker in the video. Anyway. Okay. So we want the vertical stretch of this function. Now, 2 ways to be solved. You should be able to solve it either way. You should understand how the 2 ways connect. But one is graphical, one is algebraic. Here's an algebraic solution, here's a graphical solution. I suggested that you graph both functions. And not everybody was doing that, but everybody, or almost everybody, did that. So right here's our basic exponential function. Here's our table. I said You should be able to write this down in less than a minute, including the graph, okay? Now, implicitly, we understand this is 1, this is 2, 1, 2, 3, 4, right? Because that's the way we graph the basic function. If you're graphing it the way Open Math does, they go out to 3 or 4 here, and who knows how far back. You don't really need any more than -2 to 2 for most problems. That gives you the shape, and then you can get it. So we graph the basic function, and then we graph our function. I assumed A was 3.5. I don't think anybody has 3.5 letters in any of their 3 names, first, middle, last. But, so it's not going to correspond to the number anybody would have used, okay? But of course, we could give you something besides one of the integers. Back to the positive integers. Okay, so here's the graph. Here's the 0.07 halves. That'd be the 0.0a if it was 7 halves. Okay. So here's a graph of y equals 2 to the x. And we know that this is a vertical stretch of the 2 to the x function. So this is y equals a times 2 to the x. There's a vertical stretch of the basic function is of the form y equals a times 2 to the x. The general vertical stretch of this function. You multiply every y value of the 2 to the x function by a, giving you the function y equals a times 2 to the x. Well, now if we do that, we see that the 0.01 is vertically stretched all the way up to here, right? Meaning every point is vertically stretched by whatever that factor is. Well, what factor do we have to multiply by 1 to get 7 halves? Well, 7 halves, right? Okay. There's not really a duh. You have to understand that. But once you understand that, it's obvious that if the y coordinate here is 1, and the y coordinate here is 7 halves, then it's been vertically stretched by that much. If it is a vertical stretch, now if it's a vertical shift, that's going to be a little different, and you encountered that. Okay, so our logic is the 0.01 stretches to 0.7 halves. So the vertical stretch factor is 7 halves. Your y coordinate has been multiplied by 7 halves. That's what a vertical stretch does. So that your y equals a times 2 to the x is y equals 7 halves times 2 to the x. And there's the equation of the exponential function with an asymptote at the x-axis. That's kind of implicit. It's really stated, but it goes through this point on the y-axis. So if you know the y-intercept and you know you have an asymptote on the x-axis, it's very easy to figure out what the function is. Okay. Next off, problems in your homework where your asymptote wasn't the x-axis. So I'm not sure what Open Math told you to do, so we were able to get the right answers, but many of you did. Okay. Connect it. That's what we're doing here. Connect it with just this one fairly simple transformation. The other way to do this, and some people approach it this way, your algebraic solution, well, y equals a times 2 to the x because it's a vertical stretch of y equals 2 to the x. That we given in the problem. So if y equals a times 2 to the x and y equals 7 halves, when x equals 0, which it does if that's the value of your a function. And of course, you have values might be 6, maybe 5. Okay. Then y 7 halves and x equals 0, so we can just write down 7 halves equals a times 2 to the 0. And we've done this. Okay. And then we just work that out. Well, 2 to the 0 is 1. Maybe I don't want to remember that any number to 0 power is 1. You tend to forget that. It hasn't been drilled into you in high school very well. Okay. Should be. Okay, so we get a equals 7 halves, so y equals 7 halves times 2 to the x. There it is. Algebraic solutions real quick and easy. Then you might be able to visualize it too, because the visual picture is at least as important as the algebraic picture. You do the algebra, you don't really know what you're doing. You don't really know what you've done geometrically. You don't really know what's happening in that graph. Okay? Now maybe you do, but you don't necessarily know just by doing the algebra what's really going on. Okay. So it's a big challenge. Of course, this is a support course for pre-calculus. So I didn't make this real hard. I could have put a vertical shift on it and then a horizontal compression. Okay. And of course, you did that for homework. So you want to be prepared because exponential functions are coming at you soon. And the more you know now, the easier it's going to be to understand what you see when you get to it. Okay. Now, where's this? Here. Okay. So. Here's your y equals 2 to the x function. Here's a table for the y equals 2 to the x function. Okay. I don't know when I'm recording, when I'm not. Hopefully we got what we just got. But okay, here you got the y equals 2 to the x function. Here's a table. Can you make a table for the inverse function? You remember how to make a table for the inverse function? You just switch the numbers into two columns. So and that's going to put 1/4 here, 1/2 here, 1, 2, and 4 here. -2, -1, 0, 1, 2 here. Well, you can graph that. Here's 2. Here's 1. Now we also need 4. All the way over here to there's 3, here's 4. And we're going to need 1/2 and 1/4. We want to locate these points very accurately. Our y values are going to go from -2 to 2. Okay. There we have it. Now we can locate these points. 1/4, -2. Well, here's 1/4, there's -2. So we'll come down here. There's our point 1/4, -2. Our point 1/2, -1 is going to be here. Our point 1, 0, well, that's right here. Our point 2, 1 is going to be here. And our point 4, 2 is going to be way out here. Now we'll do a nice smooth curve. There's our graph. Okay. Now, the inverse of the 2 to the x function is the log base 2 function. So this is y equals log base 2 of x. Now, it's kind of helpful to compare this with things that we did inverse function. Remember, yeah, that was done in the first couple of weeks. Okay, chapter 1. So you might want to review it because it's going to be important. Okay, I might as well go ahead and graph at least part of the exponential function here. I don't have a place for the 0.24. But the 0.12 is here. And of course, 2,4 would be up about there. So here's y equals 2 to the x. Here's y equals log base 2 of x. Okay. Now these kind of seem to be kind of opposites in some way. Where this thing has an asymptote at the negative x-axis, this one has an asymptote at the negative y-axis. Like this point corresponds to this because all we did here was we reversed the x and y coordinates. If we reverse the x and y coordinates, then the point negative 2 1/4 becomes the point 1/4 negative 2. And same thing here. Same thing here. Same thing here, and the same thing here. Now, if this graph is drawn accurately with equal scale, then the line y equals x will split these graphs right in half. Okay. And every one of these lines here will cross this horizontal x line at a right angle. Now, things got a little distorted here. That's not a good right angle. Okay. But yeah, these aren't too bad. This one isn't too awful. This is pretty awful, but it's at that point where I needed it. Okay. A little stretched up here. Okay, well, that's the picture. I think your book is going to tell you that. What is for some reason I want to write this in blue. What's the log base 2 of 2 to the negative 1? Think on that for a minute, see if you can get it. Okay, log base 2 of 2 to the negative 1. Well, 2 to the negative 1 is 1 over 2 to the 1. Now, people are still somewhat confused on these exponents, and you really can't be. You have to understand negative exponents. Review it, whatever. Anyhow, that's log of 2 of 1/2. What's log base 2 of 1/2? Well, you've got a table up here and you've got a graph down here. 1/2, negative 1. Okay. You find it from the table. Right there it is. You can find it from the graph. Log base 2 of 1/2, you find 1/2. And then you go to the log base 2 graph and you see it's negative 1. Okay. Also, you can see that you have the point before you write. And of course, that corresponds to the point (1/2 negative 1) on the log graph. Okay. So you got all these connections. You got that, and you got this. And you got this. You project from 1/2 onto the log graph and project over to the y-axis again, negative 1. You want to understand that in every possible way. Okay. So it's log base 2. of 2 to the second. Click on it, don't say anything. Okay. Log base 2 of 2 to the second, well, 2 to the second is 4. So we can see 4 here, and we go up to the graph and we see that we get 2. In other words, when x equals 4, so log base 2 graph tells us that the log base 2 is equal to 2. Okay. Now the table also tells us, okay, log base 2 of 2 squared equals 2 from the graph, or log base 2 of 2 squared is log base 2 of 4 equals 2 from the table. Okay, well, in general, there's sort of a pattern here. What's log base 2 of 2 to the x? Well, we saw that log base 2 of 2 to the -1 is -1, right? And log base 2 of 2 squared was 2. So it looks like this number over here tends to match the exponent, right? Well, log base 2 of 2 to the x then equals x. Has to, because these are inverse functions. Okay. I'll remind you that this is as a form. F of f inverse of x is always equal to x. Well, we could say that this is your f of x function. This is f inverse of x. And you want to connect things with what we did in chapter 1 when we talked about inverse functions and solve to get inverse functions and all that kind of stuff. Okay. Well, there it is. But now we've got a rule, and we can actually expand this. So we can expand it a little bit. So now y equals b to the x, that's an exponential function with base b. Okay, you've had an introduction to that. You understand they have, if b is greater than 1, you have a graph that looks much like this. Okay. If b happens to be less than 1, your graph is going to be like this. Well, we did that for home. Should be familiar with it. In the case of a function like this, well, I we're just handling. So I'm not going to do it, but you'll see. Okay. So log base b of b to the x equals x, and b is log base b of x equals x. Now logs have other properties that I'm just going to kind of list. I'm not going to try to pull these properties out of the graphs, although we could. We're not going to take the time to do that. Maybe you'll do that in your free calculus course. We'll probably do it in my section. Okay, with our other sections, choose to go the geometric route is up to them, because everybody makes their own decisions about what to emphasize and how to approach the material. And that one isn't any more valid than the other, unless it's mine. No, my decisions aren't any more valid than anybody else. Okay. In some cases, probably less valid, who knows? But I choose to get a look at the graphical meaning for these things. But here are some properties. I shouldn't use A and B like that. I'm using B for the base and B for one of the numbers. And really not what we want to do. So I'm going to go like this. I'm going to use log base B of x times y, where x and y could be any numbers. Okay. If your numbers are multiplied, then you take their logs and add them and you get the same thing. Okay. And this is because for the law of exponents, it says b to the x plus y equals b to the x times b to the y. I'm not going to spend time right now explaining the connection here, although it's not hard to explain. Okay. We don't want to take the time with it because we're just trying to get used to these rules. Okay. Log base b of x raised to the y power is y times the log base b of x. Raising to a power, then the log becomes a multiplication. Okay. This is because there's a reason for it. Make sure you understand these rules of exponents. B to the x raised to the y power is b to the xy power. That's your basic rule that you can easily understand by simple examples. Okay. And we've been over this. So I want to review it if you want to have a little deeper understanding of these things. But those are the rules. Okay. Also, log base b of x is the log log of x divided by the log log of b. This is handy because you have an log log on your calculator. this is what you have to do to find the log to the base of a given number. You divide the log of that number by the log of b, or if you want, you can divide by the natural log. So that's still the natural log of b. These are your rules. There's a little more here. Your book includes a rule: log of x divided by y is a log of x minus the log of y. Okay? Just like multiplication, you add the logs. For division, you subtract the logs. I don't think it's necessary because if you understand -1 powers, you can use this. Now, x over y is x times y to the -1. Okay? The log of y to the -1 by this is -1 times the log of y. So you have log of x minus log of y. Right? Always, from the very day I saw these rules, I thought that one was redundant, but it's always stated. Because I guess nobody wants to actually make you think much. And when you're first, there's really a point to it, okay? So my take is a quick only process take on this. When you're first getting used to this, you don't want to think about too much besides this. Okay? Yeah, I've heard there's a terrorist lurking around here. Anybody seen anybody? Just Danny. Danny, a great guy. Yeah. Lead guy in there. He's a student on the go. Okay. So, make sense? I'm taking a risk consulting Danny like that on don't let him know. Okay. What good is this? Well, that's obviously a rhetorical question that I'm going to answer. At least part. It's a lot of it. And I meant it was just good. Over there. Okay. Let's say we want to solve the equation. Okay. If we want to solve this equation for x, that 1.7 to the x equals 12. Okay. Now, turns out that using these rules of logs, that's a really easy equation to solve. So let's see how that works. Okay, well, we can say that the log of 1.7 to the x equals the log of 12, can't we? Okay. Well, by the rule, what does the second rule say about log of 1.7 to the x? Can you write it down? Apply the second rule to the left-hand side of that equation. The second rule says the log to the base b of a number to a power is equal to that power times the log of the number, right? So the power here is out front of the log. So it's a little confusing that we have X's and Y's there and we have an X here, okay? But what this says then is that X, piece of chocolate pens me once more, it's going on a trash can. X log of 1.7 equals the log of 12. Now, what do we have to do to both sides of this equation? Solve for X. If you just did this, then that's good. Then the next step could be a little confusing because there's a tendency to want to do something you just can't do, okay? So you got to divide X times whatever it is by that thing so you get X, right? Of course, if you do that on one side, you do it on the other. So X is the log of 12 divided by the log of 1.7. Okay. Now, there's a tendency to want to then divide 12 by 1.7, but logs don't cancel out. A log is not an algebraic quantity, it's a function. And unless the log is not only a linear function, but a linear function whose graph goes through the origin, okay? It's not going to work. So you have to find log of 12. Go got a calculator. Everybody find log of 12? If you don't have a calculator, it's okay. Log of 12 is a little more than 1. Okay. I'm not even going to try to estimate it because it's so close to 1. 1.0 something. The log of 1.7 is a little easier. It's about maybe 0.27. Mark. What's the log of 12? 1.06, 7, 8. Okay. Okay. So what it tells me it's 1.08. And the log of 1.7 is what? 0.23. I thought 0.27, but that's hard to interpolate. Incidentally, the LOG log is the base 10 log, as you'll see. Now, we could have used natural log. That's actually a little easier to estimate because it's a smaller base. Anyhow, that's about 4.3 maybe. Not my day for good estimation. Comes out something like that. Okay. And I'm getting a nod there, so maybe I was actually close. Okay, so that's basically how you're going to use logs to solve equations. Okay. Now, another way of saying it is I'm going to use X here. E to the A equals C. Then log base B of C equals A. And vice versa. Making this an if and only a statement. Now, we could have used this to solve this equation. We just, our x is in the exponent, right? And we can't get it out of the exponent except by taking the log, okay? Well, taking the log is equivalent to doing this. So So if we use this rule, then for this equation, which form is this equation in? Is it in this form or this form? First one or the second one? Well, this got a log, right? Does this have a log? Does this have a log? Since this one. Okay. So in this form, and let me do log base. This LOG is a log base 10. Let me stick the log base 10. Same solution. That I do. Okay. LOG means log base 10. But in order to apply these rules, we've got to have a base. So we're going to have to write the 10. Okay. So in this form, what's B, what's C, and what's A? Write it down on your paper. C equals B equals A equals. Okay, for this expression, what's B? B is the base of the log, right? Well, B is 10. What's C? Actually, I phrased this wrong, okay? I need a little more space over here. I jumped ahead of myself and I apologize for that. Actually, our equation (1.7) to the x equals 12. That's trying to force something into the wrong form. That was kind of pretend you never saw that. Okay. Our equation is 1.7 to the x. This is in the form b to the a equals c. Okay, so that's the first form. Okay, what I wrote down here was not in either of the forms, but could have been put into one of the forms. But we start with the original equation. Okay, b to the a equals c. Well, what's b? B is the 1.7, right? A is x and c is 12. Okay. Again, I apologize, I wrote down a step in this solution without even thinking, okay? So that's what we see. Well, this is the same as what? Log base B of C equals A, right? Because this form is the same as this form. Okay. Now, substitute B, C, and A that we found in this form here, and see where that leads you. Okay, now, maybe I didn't stop the recording. Okay, but what we have is 1.7 to the x equals 12 in this form, b to the a equals c. That's this form. With b equal 1.7, a equal x, c equal to 12. Your b is the base, your a is the exponent, and your c is the particular. This is the same as log base b of c equals a. So log base 1.7 of 12 equals x, because b is 1.7, c is 12, and a is x. Okay. And of course, the log of 12 over the log of 1.7 equals about 4.3. Okay. Now, got time for one more equation. Let's say we have badly written, but it's 100 times 1.05 to the 2 equals 200. Okay. Is that in this form? Is it in this form? Or is it not in either form, but could easily be put into one of the forms? It's not in either form because you do have like a 1.05 to the t, which means you're looking at this, but you don't have a number in front of b here, right? So it's not quite in that form. You can't have a number in front of b. So what we do is put it into the form b to the a equals c. And that's easy enough. Take 100 times 1.05 to the t and divide by 100. We'll go over here. We divide by 100. Okay. And that gives us 1.05 to t equals 2. So b equals 1.05. A equals t, and c equals 2. So this is equivalent to log base 1.05 of 2 equals t. Just plugging those into this second form, which you get used to. So t is log 1.05 of 2. Now I can actually kind of cheat here because there's a rule applied to compound interest. I say this is kind of close to 14. Okay. Well, yeah, let's write out equal to and if you calculate this accurately, which you can do with your calculator, you find that this is approximately 14. The significance of this is, and I've been over the details of this, if you invest $100 at 5% interest compounded continuously, this is the function. It tells you how much this thing is worth after 2 years. Okay. And 200 is twice as much as 100. So your actually solution to this tells you how long it's going to take your money to double at 5% interest compounded continuously. Okay. And this says it's going to take 14 years. So in another 14 years, it'll double again, you'll have $400. And hopefully that's ahead of inflation, which wouldn't be the case right now. Hopefully that's going to settle down. Tricky situation. Okay. So one of the main applications, one of the most important applications is being able to solve an exponential equation. And of course, logarithmic equations are important too, and you'd solve those by converting to exponential form. This is the logarithmic form of an equation. This is the exponential form. It's like an exponential function. This is like a logarithmic function. Okay. Well, now all the stuff that you learned in the assignment for Thursday is relevant to solving exponential and logarithmic equations. And you're going to be working with the properties of logarithms in ways that I haven't been able to completely go over, but I wanted to give you a picture of why it's important and how it's really used. Okay, so work through some details and we'll talk about some of those next time.